Hello everyone, welcome to Python Challenge for All. Okay, so today I'm going to present you a special topic video series entitled Invitation to Fractal Geometry. I hope you'll enjoy it. So Invitation to Fractal Geometry, subtitle is Infinite Forms from Self-Similarity. Okay? Maybe you know what fractal is. So what is fractal? The word etymology. The word is derived from the Latin word fractus or fractus. Okay, meaning broken or irregular. Okay, the proponent who first proposed the concept is called Benoit Mandelbrot. I guess he was a Belgian. In 1975. It is a concept first invented by Benoit Mandelbrot, and it's like very interesting self-similar geometry. Okay, so we can think of many interesting shapes, which I will introduce from now. Okay, about Benoit Mandelbrot. Where is Benoit? Okay, we have very many. Okay, this guy, very big name, who had a Polish-born French-American mathematician. So he had a very hard time during the World War II, I guess, because he was in Poland. Anyway, he did a great job after moving to the United States. Yeah, he was born, from Warsaw, Poland. Okay, anyway, so let me go back. So fractals, the core concept is self-similarity, a property where parts of a figure, when magnified, reveal the same shape as the whole. So this is what fractal means. And we will enjoy both appreciating and drawing ourselves from now. Fractals in nature. So we have in real world a lot of examples, like in the next page. Yeah, you know this fruit, vegetable? You know this. This is, Romanesco. Romanesco, cedar, cedar trees, pines, or river patterns, snowflakes, or tree structure. These are real beautiful fractal examples. Okay, so natural formations are closer to fractals rather than smooth Euclidean geometry. That's an interesting part. We learn about very beautiful Euclidean geometry, but in fact, in the real world is rather on the side of fractal geometry. Okay, so plants, geography, weather, biology, those are all better described as fractal figures rather than Euclidean geometry figures. Let's take a look. So very positive, starting point can be Koch curve or Koch curve. In Japanese, it's Koch curve or Koch curve. So it's very simple. Prepare line segment, divide it to 3 parts, equal length, and then have an upward spike in the center of the regular triangle, okay? 正三角形形にこう, okay? And then do the same thing for each segment, okay? Do the same thing for this segment, do the same thing for this segment, and this segment. It's like, and continue all the way, doing the same thing for all the small segments of the same length here. This is called Koch curve. Using Turtle, it's very easy to draw Koch curve. Okay, so let me take a look. Yeah, I will later explain about Koch curve implementation. Let me show this implementation. And again, here is a pointer to the Diadon Python or Python challenge for all lesson names in my video series. So let's take a look at, say, Koch curve. So very simple Koch curve can be, let's see, where is it? Fractal tree Koch curve. Okay, yeah, this one. So this, as you can see, it is very easy using Turtle. I hope you are familiar with Turtle graphics. So it's like only draw a line forward of S length, okay? So the Koch curve can be defined as a recursive goal of Koch function, which uses dimension n, and second parameter is line length S. Okay, so if the n is 0, this is the terminal case, we just draw a single line segment of length S and return. Otherwise, we call Koch of n minus 1, S over 3, 1/3 length of S. This is like calling this line, okay? And then turn left by 60 degrees. Turn left by 60 degrees. Do the same thing, Koch n minus 1. And then turn right by 120. Here, we turn right by 120 degrees. And draw a segment. And turn left by 60. Turn left by 60. And then draw Koch n minus 1. This is all, okay? By using this, we can draw a line of any level, okay? And by connecting the 3 of these Koch lines, we can draw what we call Koch snowflake. So it's like having 3 Koch curves, and each one being the Koch curves. Okay, so yeah, we can do Koch 0 is just simply this one. Okay, Koch 1 is this one. Okay, right? Each segment is just like this one. And then the second one is more complex. Okay, and we can continue this until yeah, any degree of complexity. So the variations are, here we use 60 degrees at the base angle, but we change this to say 85. We call it, say, Cesaro curve, or we can define other variations as Levy curve. So instead of drawing, say, like this, we can, for example, draw with rectangle shape like this, or we can use this, which, yeah, each will produce very interesting shape. Let me just briefly show this. If you change, say, instead of this, let me save as Cesaro.
Cesar.
Okay, and instead of having degree is like 60 in this case, a times 2 and a. So this is very simple. This is the same. Let's, instead of writing this, let's think of just a single line. So this is Koch curve of, so set level 2. Okay, if you change this to say 85, we can enjoy this kind of strange shape. Okay, so each one is changed to 1. So let's do it. Let's increase this to say 6 and increase the length to say 400 or 600. We can have very interesting shape. We should have longer. Okay. So this is maybe 6 is too big. Let's think of 5. So yeah, this is a very interesting shape, right? So yeah, the whole thing is triangle, but here only the same shape appearing here and there, and from both sides, and producing a very interesting shape. This is called Cesar curve. Anyway, so we can enjoy all the variations if you like, or like this, okay?